Good afternoon, everybody. My name is Emilio Boza. I'm the president of the Scientific Council. Before starting, I would like to welcome you to the Foundation on behalf of the patronage and the direction of the Foundation, Ramón Areces. You're welcome to the 16th conference. It is a regular activity that we have repeated during the last 16 years in collaboration with Springer Nature. Springer Nature works with us, proposing on a yearly basis a number of topics. And then the Foundation chooses one. The proposals are generally discussed, but in this instance, it wasn't. Unanimously, unequivocally was chosen, and immediately we picked dementia, because after all, it is a question of concern to everybody. The greatest concern of human beings is what we popularly call as going insane and losing your head. So, this kind of disease and a different point of view, you don't come seeking help for yourself, but by others, by the ones around it, detected by others. It is what we call in medicine a syndrome, not a disease. And a syndrome will be a set of clinical manifestations which are common to many different pathologies. So in this entity, the Alzheimer's disease plays the predominant role. It is the protagonist. It accounts for 60% of all dementias. But it's not the only one. And it is very pertinent to discuss the disease. Now we start to see the light at the end of the tunnel. If we were Sicilian, we would say this is not the beginning of the end, not even a glimpse of the end, but at least the very tail of the end of the story is barely emerging. There's new diagnostic possibilities. We're working on that with biomarkers. We're going to discuss this afternoon. And more importantly, there's light being shed in the tunnel, even more than just a light in therapeutic perspective. So I know it's going to be a really interesting meeting. I have to introduce Soledad Santos, which is the editorial director for Iberia and Latin America, to introduce the meeting and the speakers. And at the end, we will have a very interesting discussion, a Q&A session with all your questions or the questions that the speakers may ask to each other. So thank you very much and welcome to the Ramón Areces Foundation. Welcome. Welcome to the 16th Science Conference of the Ramón Areces Foundation and the Springer Nature Publishing Group. It seems that time flies, right? It was quite long ago, and we thought maybe we'll run out of topics or that our presentation becomes obsolete. But year after year, the auditorium is full. Today it's raining, and there is no audience. So we believe in this Springer healthcare nature business. It is our duty to propose topics that bring us closer to the latest advances of research concerning society at large, of course, such as neurodegenerative diseases, which we will visit today, dealing with dementia, or in the past with the artificial intelligence and other issues. So it is greatly satisfactory to continue with this collaboration and contribute to the growth and diffusion of scientific knowledge with the Ramón Areces Foundation and Springer Healthcare. So we really thank the Foundation for this opportunity, and we thank the Scientific Committee represented by Emilio Boza for choosing so pertinently the topics and speakers. We also like to thank Mr. Raimundo Pérez Hernández Itorra and Mr. Azcona, directors in the Foundation, for their trust in us to continue organizing these meetings throughout the years. My aunt, Esperanza, was a great cook, and at family meetings, all the cousins were expecting her dishes, her exquisite dishes, but a few months ago, we have to watch her over the kitchen, and now, little by little, she's forgetting her wonderful recipes. The mother of my friend Rose forgot she had children, and she called the eldest Uncle Louis. Well, like many others, there are millions of inhabitants suffering from dementia, and there will be a threefold increase by 2025. And dementia, of course, not only affects patients, but everybody surrounding them. The heavy impact of this condition has triggered the WHO for a palliative plan, the first one to be drafted for a non-transmissible disease. The title is Conquering Dementia. And we use the gerund because we know there's been a lot of advances, but we still have a great room for improvement. So from Springer Nature, we want to have the publication of 180 books and 11,000 articles devoted to this topic, Nature, Aging, and Drugs and Aging, are magazines devoted just exclusively to aging, and therefore always are in contact with dementia. And then we will think about medical advances and social implications, because we know about the largest impact of dementia. We invited Bart Distruper, who will bring us closer to the molecular basis, and this will all help us design better strategies for the future. In diagnosis, Gemma Salvador, one of our national leading researchers, will explain the advances as to biomarkers detectable in blood or other fluids, which will facilitate accurate diagnosis. And dealing with treatment, we will learn about the latest advances with biological agents for the initial stages of the disease by Alberto Llegó. And finally, what about the prevention of dementia with different feasible actions and policies? Jill Livingston will show us the results of her preventative programs that have yielded very hopeful changes and have inspired many changes in healthcare systems. Thank you very much, Jill, Alberto, Gemma, and Bart for coming to Madrid. And finally, I thank Erika Pastrana, the National Director of Nature, for moderating this event. It's been many years that we've enjoyed your professionalism. We hope to go on doing it in the future. So thank you very much, Erika. I hope you enjoy the presentations and the debate afterwards. I'll give the floor to Erika Pastrana.
Buenas tardes a todos. Yo también quisiera empezar.
Good morning, everybody. I'd like to start by thanking the Ramón Areces Foundation for organizing these events. The general public may come to listen and enjoy this opportunity, listening to international experts discuss the most relevant advances from a clinical, social, and scientific point of view. I thank you all for coming here today, and I encourage you to participate with your questions in the debate. Dementia is one of the greatest challenges from a healthcare point of view in our century. And as my colleague Soledad said, it is very devastating as a disease because little by little, creeping insidiously, it removes the most fundamental characteristics of a person: memories, self-confidence, autonomy. The incidence rates of the disease are not positive at all. The worldwide number of inhabitants are 55 million, which is greater, for example, than the number of people suffering from cancer. Alzheimer accounts for 60% of the dementia cases, and it appears in 10% of the people of 65 years of old or older, and in 50% of over 85 years of age. So it's very clear. All of us will be very close to dementia or Alzheimer, either in our own bodies or in somebody very close to us. It's true that the figures are frightening and staggering, but there is a little hope, particularly now. That's why I'm so happy to introduce today's speakers. One of the good news of the disease is that in 35%, it is believed that in 35 cases of dementia cases could be prevented with policies acting on education, management of cardiovascular diseases, exercise training, and social contact. In the last years, there has been a great hope with the latest therapies newly approved that at last are mitigating the devastating cognitive symptoms of the disease. And then we will have advances in biomarkers. Finally, we can detect the disease before the symptoms have truly taken possession of the brain. We have 4 international speakers to discuss these advances. We will listen first to the 4 presentations and then the debate and the questions afterwards. And so if you have questions, write them down, because at the end there will be an opportunity to ask these worldwide experts. So let's profit from their knowledge. Now, without further ado, Dr. Bart de Strooper. Dr. de Strooper is a molecular medicine professorship in Leuven in Belgium. He is the founding member of the QU Research Institute, and his research is focused on the underlying mechanisms to Alzheimer's disease and Parkinson's disease. His main findings are the identification of gamma secretases and his role in the amyloid precursor protein proteolysis. His group also has worked in identifying the cell types involved in the disease, including microglia and astrocytes. And he received many awards, and Bart de Strooper received the highly prestigious Brain Prize 2018 for the genetic and molecular basis underlying Alzheimer and Parkinson's disease. So, Dr. de Strooper, you have the floor. Thank you.
So thank you very much for the introduction, and it's really a pleasure to be here, and it's also a pleasure to talk about neurodegeneration. A couple of years ago, it was really sometimes frightening to come before a public and talk about all the work we did without much less concrete to show, and I think today we celebrate partially the first points of light, as the previous speakers also have said already, but it is indeed still a lot of work to be done. So just stressing further what the other speakers have said, neurodegeneration is really a big, big problem. And it's not only in Spain or in Europe or in America, but it's a worldwide problem. And what you see here is the number of the increase of this disease all over the world in the next 30 years. And you can immediately see that the race is not only in Europe and America, as I said, but the main race will be in developing countries where also the public or the people become older and older. And so I like to think about this problem as a worldwide problem, and if we make medication, or if we do something about it, we should do it for the whole world. So I would like also to start with some general things, things which are not so well known. So people ask me, after 30 years in the research, why don't you have more solutions? Why don't you have cures, etc.? Well, the brain is a very difficult organ, and we can talk about that maybe in the questions. So that's certainly one excuse. But the other excuse is underinvestment. And so here you see the number of publications we have for AIDS. So one terrible disorder started in the 80s. We didn't know what it was. A couple of years later, there were about 8,000 publications per year published on AIDS. In the meantime, we have medication. So for Alzheimer's disease, which was a disease which was already there in the late, well, it has ever been there, not like AIDS, but you see only in 2015 we got a similar number of papers on neurodegeneration as for as for AIDS. So we are now going in the good direction, but we have a long distance between the research in AIDS and in Alzheimer's. But I think the problem is even bigger. As was said already in the introduction, the number of people with dementia is larger than the number of people with cancer. And so I compared the knowledge basis for cancer with the knowledge basis for Alzheimer's disease. And you will see I have to adapt this graph. So that's about the situation. So we know 18 times more. Every year there is about 15 times more publications about cancer than about Alzheimer's disease. And if you see the cumulative knowledge for cancer and you compare that with the cumulative knowledge for neurodegeneration, then I think this is probably the major explanation why we don't have much more progress than we do. And it also tells us that it's high time that we start to catch up. Last point I want to say here is I'm not saying that cancer has to be less money. That's absolutely not the thing. I think cancer shows what can be done when there is a continuous investment in an area of disease, and I think that we should do the same effort for neurodegeneration. So a third point I would like to clarify, and has been really a difficult problem, a difficult issue for the research and also for the medical development, and that is permanent confusion of Alzheimer's disease and dementia, or dementia and Alzheimer's disease. So dementia is a symptom. It's like fever. It's something which happens, which shows that your brain, this computer, doesn't work very well. But it's a symptom, it's not a disease, and we cannot say we are going to cure dementia. We'll never be able to cure dementia. What we can cure is the underlying disorders, and Alzheimer's disease is one of these disorders. And so here you see a graph. It has already been said that 60% of dementia is Alzheimer's disease. I don't agree with that. I will explain you in a minute. But so globally, if you look in the brains of patients who die from dementia, you will see in 60% of the cases Alzheimer's disease lesions, amyloid plaques, neuronal tangles. But there are also many other causes of dementia. And I think one of the more underestimated causes of dementia is vascular dementia, which if you look to the brain, it's one big bundle of blood vessels, and that's because your brain is the big user of oxygen. And so if it's not good with your heart, it will not good for your brain. So, but let's come back to the 60% Alzheimer's disease. I agree that in 60% of the patients you will see amyloid plaques and neuronal tangles, the typical signature for Alzheimer's disease. But in more than 60% of the 60%, there are also other lesions, like Parkinson's disease, alpha-synuclein, TDP43, etc. I'm not going to go too much in the specialization here, but there are lesions of other neurodegenerative disorders. And so the point I want to make is that in most cases, which clinicians call Alzheimer's disease, we are looking to a mixed form of dementia, a mixed form of neurodegeneration. And if you want to cure these patients, we will have to treat each disease separately, which is not unusual for old age, that you have several diseases in parallel. But there is no miracle, there will never be a miracle where you can solve all the problems with one drug or one approach. So that's very important that we realize this too. And then I say Alzheimer is not dementia, it's also not always coming up as dementia, and that's also something important. So you need to realize that the symptoms are a consequence of the particular brain region which is affected by the disease. And here you see a form of Alzheimer's disease which has not manifested itself as a memory problem. So you see here in the circle, you see here a brain, of course, from a patient, a scan, and you see there the preserved hippocampi. This is the area which is normally degraded in Alzheimer's patients. That's the seat of the memory. But in these patients, there is not much problem there. But if you look to the other part of the brain there, the posterior side of the brain, that's where the visual system is operating. So you see that there is a big loss of gray matter there. So there is atrophy in the visual cortex. And these patients, they come to the clinic complaining that they don't see very well, and the ophthalmologist doesn't see any problems in the eyes. And it's only years later that the visual dementia, you call it, but the Alzheimer's disease in the visual system spreads out over the brain, and then these patients present with dementia. So again, illustrating you that we should get away a little bit from that narrow focus on dementia and study this as a disorder which can affect different brain areas, etc., etc. So I think that one of the major steps forwards we do in the field is that we are moving away from a taboo to a disease, that we are starting to understand that this is not fate, that it's not because you become old that you have to have a degenerated brain, that we start to fight against that idea. And one of the best arguments is the centenarian cohort of a colleague of mine in Holland, where she follows hundreds of patients who become 100 years and older, and which have a perfect cognition. So age increases your risk for neurodegeneration, for dementia, but it's not the cause of it. It's a factor which makes it more likely, but it doesn't need to be like that. And that's a very important realization. I think that has also been very important when we started to find cures for AIDS or for cancer, that we went away from the taboo and that people start to talk about it as a disease, not as something which you don't mention. And I think this is changing at the moment, which is a good thing. So what is Alzheimer's disease then? Well, we go back to the roots, Alois Alzheimer and Oskar Fischer, from the time that professors really looked like professors. They defined this disorder by looking in the brain of patients, and they see these 3 lesions. And so it doesn't matter, you don't need to remember these names, but you see these brown precipitates here, which we call the amyloid plaques. And then you see this black, dark, ugly stuff in the brain, which we call neurofibrillary tangles. And then you see something which is mostly forgotten when people talk about Alzheimer's disease, but it's also always present, and is granulovacular degeneration, basically saying that there are neurons dying, etc. It's also an important sign of the disease. And so I would call everybody who has these lesions in the brain, even if the person looks perfectly normal, I would say this person has Alzheimer's disease. And we need to treat that, because it will end badly. Of course, some people have fantastic genes and will die before you get dementia, but I think the most of the people need a treatment when you have these lesions. So the last point I want to make as an introduction is that this is a very slow disease. This is something which happens over decades. And in this graph, it's a bit complicated, but I will see when my pointer works. Yeah. So what you see here is the beginning of the disease. You get an accumulation of this amyloid peptide, these amyloid plaques. And that takes quite some time. And then you get the other lesions, the tau lesions, which start to accumulate. And then you come more close to the clinical phase. It's the symptoms where the brain gets damaged, and what you can see then clinical signs of Alzheimer's disease, etc. So it's a slowly progressing disease, and the most important thing is the 30 years which are indicated there. It's an approximation. We don't know exactly how long it takes, but we know that 10, 15 years before you see the first clinical signs, there are already these biochemical and anatomopathological lesions, which I just showed you, are present there. And so even with Alzheimer's disease, when you have the first clinical diagnosis, the mean time from the first diagnosis until death is 8 years. So this makes it very difficult to investigate it and to investigate the effect of drugs, but it gives us also hope, because if it's such a slow disease, you can probably treat in a moment that there is no clinical symptoms yet, and you can probably also treat the disease not by curing it, but by slowing it even more than the intrinsic slowiness of this disorder. So what causes Alzheimer's disease? And I'm sure that all colleagues will agree, but I always reflect on this twin study. And twin studies are very good because you have identical twins, which have identical genes, and you have then the non-identical twins, which are brothers and sisters, and which have mixed genes, but a shared environment. And it's complicated studies, but this is really a big one with 12,000 twins. And just to make a long story short, the conclusion of that paper is that you have about 2/3 of your risk for Alzheimer's disease is genetics. So it's the genes you get for your father and your mother which largely determines whether you will die of Alzheimer's disease or not. Of course, genes is one aspect, environment is another aspect, but the difference with, for instance, Parkinson's disease is that in Parkinson's disease, the genetic risk is estimated about 20%. So environment in Parkinson's disease is much more important than in Alzheimer's disease. And so this is a very complicated map. You have to look to it like a map. Don't get confused. It's a map with all kinds of data points, and we use that in the lab to understand genetics. But I just showed this in the first place to impress you with the enormous progress we have made in understanding the genetic basis of Alzheimer's disease. And so just to make this a bit more clear, what you see here in the bottom is the frequency of these genetic mistakes in the genome, in the population. So you come from very rare cases to very abundant mutations of changes in the genome in the population, so up to 50%. And then you see in this axis the risk of Alzheimer's disease in this axis. So here, very high risk. If you have such a mutation, you are sure to get Alzheimer's disease. If you have here these mutations, your risk increases a little bit for Alzheimer's disease, or it lowers it a little bit. And then you have genes like ApoE4, which increase your risk 3.5, 4 times, which is a moderate increase in risk. So we have learned a lot from these genetics. And so the genes on top there, which if you have a mutation in it, it's very rare. Don't think that in your family this gene is present. It's only a few families and they know it. But it's a very rare cause of Alzheimer's disease, but if you have such a mutation, you get Alzheimer's disease. And this has been really the key that has helped us to understand how Alzheimer's disease is initiated. So these mutations all create amyloid plaques. And so that's why I still think that amyloid plaques are crucial initial triggers of the disease. And this is also the reason why the field has focused enormously on amyloid plaques, and despite many trials, they continued going because the genetics were clear. And so I think that we celebrate a major breakthrough, and other speakers will talk more about it, with the first treatments which really clear the amyloid from the brain. And you see here an amyloid scan of a patient, and a year later, the amyloid has disappeared. And so there's 2 successful clinical phase 3 trials, which is the acid test for a drug, which have shown a slowing of the disease. And that's the whole thing here. So here you see the graphs, and just focus on this part here. You see here that the patients go down, which are treated with a placebo, and then you see here the effect of the drug. And so the first months, you see really almost a stabilization of this patient. So that's really fantastic. And what you would expect is that went on. But you see here, for reasons which I don't understand, and I hope one of the speakers can explain me, then you see an acceleration of the decay. And there the 2 curves come again parallel. And that worries me a lot. So I will explain you what I think. So can we do better? So I think this is the first sign of a treatment, so it cannot be underestimated how important that is. Think about AIDS. The first drugs had a lot of side effects, very little effect, but it has ended now with a story where AIDS has been cured. So I think we are seeing the same thing here. But we need, as scientists and medical doctors, continue to ask, can we do better? And I think we can do much better. So, and that's another way of looking to Alzheimer's disease. So you have this amyloid, which I think is a trigger, not a driver of the disease. And then you get the brain, all the cells in the brain, the neurons, but also the microglia, astrocytes, oligodendrocytes, all these supportive cells, they react to that amyloid. And it's your genes which determine how this reaction is. So you have microglia which are reacting positively, you have microglia which react negatively, largely driven by your genetic makeup. And then after 10 years or more, you end up in this clinical phase with brain atrophy and dementia. And so if you go from the treatments that we have now work here, but we test them here. And so you might do a little bit on the biochemistry here of the disease, but the cellular phase is probably acting on its own. And so what we need is, first of all, bringing these amyloid drugs much earlier like cholesterol for atherosclerosis, we need to treat early, and then we need further medications. We treat the cellular phase. And so can we do that? Well, I will just briefly touch on the research we are doing. Alzheimer's is a very difficult disease to study. There is no animal which really get Alzheimer's disease, but we have mouse which get amyloid plaques. And so my question was, why does the mouse not get Alzheimer's disease while humans get Alzheimer's disease? And so we thought maybe we should bring human neurons into the mouse brain and see whether there's a difference, human neurons acting versus mouse neurons. And so it's a complicated story for the scientists here. They have to read the papers because it would take me too much time, but we have done that. We use stem cells, we make neural precursors, and we transplant them in a mouse with amyloid plaques. And we see then tangles and tau pathology, and the neurons die, which is a very good model. But you see also these blood biomarkers changing. And you see here that in this model, we get an increase of these two famous novel blood biomarkers. You will hear more about it in a minute. But this tells me that these neurons in this mouse get the same disease as Alzheimer patients. And so I think this is really very interesting. And we published that these neurons die from necroptosis. It was not known how neurons die actually in Alzheimer's, and you can treat necroptosis. So I think that's an interesting aspect, and we can probably, in my summary, I will come back to that. And then the other thing is the microglia, and human microglia, these are very little cells in your brain which defend your brain against all kinds of stuff. And so human microglia are very different from mouse microglia. And so we thought maybe we can do the same trick, and most of the risk genes are expressed by these microglia, so these microglia must do something in the disease. And so we thought we are going to use the same trick as with the neurons, and you see here a mouse brain, and every green dot is a human microglia. And so this allows us to study how human microglia react on amyloid plaques. And this paper is in press. Well, this is single cell analysis for the specialists here, but this basically shows you the reaction of these human microglia when they see amyloid plaques. And you see really here a very important aspect is this antigen presenting response. I cannot discuss it now, but so you can see that we really can mimic the microglia responses that happen in a patient, in a mouse, which allows us now to make drugs to treat this. So now the question is, of course, what in this microglia reaction is good, bad, or ugly? We will find that out. I can discuss an hour about that. But we will find at a certain moment what drug we need to do to make the microglia react in a good way or in an ugly way, which we will, of course, not consider a treatment then, but we will understand. So I'm at the end of my talk. So I'm back here to these three phases, which summarizes basically the long time of Alzheimer's disease, the cellular phase, etc. And so if you think about it, in the A-beta, the biochemical phase, what we need is a cheap oral drug, not an antibody, which we can give when you're 45, 50, just like you treat cholesterol, to prevent amyloid accumulation. We need anti-inflammatory or anti-whatever drugs which compensate for the inflammation, and also maybe this necroptosis, we could maybe stabilize the neuron for a while by drugs against necroptosis while the antibody is working, and it takes a year to clear the amyloid, so you would stabilize the neurons, and after a year when the amyloid has disappeared, you would have more neurons than somebody who didn't get that treatment. And then finally, I don't think that you can do a lot once you have dementia, but maybe with all these transplantations we do in the mouse, I'm starting to think maybe a day we can give you some stem cells made from your blood, differentiate them in neural precursors, and we can maybe restore part of your memory. But that's, of course, very far-fetched in the future. So where are we headed? This is the number of Americans which will have Alzheimer's disease in 2050. If we can postpone the disease with 5 years, which seems to me a very reasonable ambition, and we could do it with environmental factors and with whatever, but also with medication. If we could gain 5 years, we would already stabilize the number of patients. That would be a great thing, because then we don't have to bring nurses and people, well-educated people from developing countries to care for our patients, while the crisis is also in those countries. So we need to stabilize, in the first place, this problem, and then go further for a cure. And so Bill Gates agreed, so that's always good. A guy has money, and I think he has also seen that we are really at a breakthrough in this field, and he has spent some money, but I think he should spend more money on this problem. And then finally, I want to read this poem because I like it very much. I'm myself aging a bit, and so I like this very much. So do not go gentle into that good night. Old age should burn and rave at close of day. Rage, rage against the dying of the light. Do wise men at their end know dark is right, because their words had forked no lightning? They do not go gentle into that good night. Rage, rage against the dying of the light. Thank you very much.
Muchísimas gracias al doctor.
Thank you very much, Dr. De Strooper. Yes, it has been fantastic. Now I would like to introduce Dr. Gemma Salvador, who is a researcher, postdoc at the Lund University in Sweden. Dr. Salvador was a doctor in the Beta Brain Research Center in Barcelona, where she's centered in the study of the preclinical phases of Alzheimer's disease by means of the use of neuroimaging and biomarkers in fluids. Her current work consists in studying biomarkers, plasma biomarkers and CFR, in order to better understand the progression of the disease. Her main interests are focused on the early detection of Alzheimer's disease, the search of prognostic-specific markers and accessible markers, and the study of risk factors that can be modifiable in the disease. Throughout her career, Gemma has received several grants, the Marie Sklodowska-Curie grant due to the importance of her research, and awards as the Junior Faculty Award of the International Conference on Alzheimer's and Parkinson's Disease. Welcome, Gemma. Thank you very much. Before anything else, I would like to thank you, the Foundation Ramón Areces and Springer Nature as well, for inviting me today to this very interesting session. As has been said, I'm going to talk about biomarkers for Alzheimer's disease. I'm going to focus on three large groups: research, clinical setting, and also the clinical trials. This is somewhat the summary of what we are going to be talking about. A short introduction to Alzheimer's disease that Professor De Strooper has already made before. We are going to say what is a biomarker, what types are there, and also how we are using them in their different uses. Alzheimer's disease, when we are going to clinical, well, the typical thing we do is a clinical assessment with neuropsychological tests, and also we do use several imaging techniques, MRI or CT, mainly in order to exclude other possible pathologies. But nevertheless, what this does is that there is still 20 or 30% of cases that are diagnosed, not properly diagnosed, and this is even more severe when we go to primary clinics. That's why, as we will see in my talk, the biomarkers of Alzheimer can help us to decrease those mistakes or those errors, as we can see right now. This chart has been shown by Professor De Strooper before, so I'm not going to stop at it too much. But as he said, there is a preclinical phase, this one in which the participants are still cognitively healthy, but there is an accumulation of Alzheimer pathology that is the amyloid pathology. The markers can be very useful to detect this pathology before there is any symptom. I'm going to talk about the different types of biomarkers and what is a biomarker. A biomarker is going to allow us in an objective manner to measure biological processes. In this case, it's the accumulation of certain pathologies or different features that happen throughout the whole process of the disease. As Professor De Strooper said before, they can entail different cells from our brain. The typical biomarkers that have been used in Alzheimer can be classified in two large groups, the imaging biomarkers and the fluid biomarkers. Until relatively short while ago, the main biomarkers in imaging were MRI, that we will see in the upper part, and the FDG PET. And this is what could allow us to see if there was an atrophy or a dysfunction of that brain that was slightly turning off itself. But this is typical for the disease, but it can also be modified by any other cerebral pathology. That's why it was a very important advance or progress when a few years ago they developed the first biomarkers of amyloid by imaging the PET-CT of amyloid that we can see in the screen, that we can see how this pathology is accumulated in the brain with those more reddish colors that we see on this picture. In the picture, what we can see is how this pathology is accumulating in different areas of the brain, depending on the stage that we are at of the disease. And even more recently, we have the biomarkers of tau and PET. As we can see here, they allow us to see where this pathology is accumulated in the brain, and also these reddish colors and yellowish colors that we can see in this picture. As you can see in the picture, this tau pathology that is accumulated, as we've said, slightly later, the amyloid pathology, has also some regional patterns that are very different from those that we can see in the amyloid. As we will see now, those patterns are also important. But what happens with the biomarkers of the imaging biomarkers? Well, one of the great advantages is that they let us see those regional patterns. But on the other hand, nevertheless, they are very expensive. They are relatively invasive, and they require very complex infrastructure. Another of its main disadvantages, especially when we compare it with the fluids, is that we can only do one at the time. If we want to see amyloid, we have to do an amyloid PET. If we don't want tau, we have to do a tau PET. Unlike what happens with the fluid biomarkers, what we do is that we take out a little cerebrospinal fluid from the bone marrow, and there we can measure different proteins. But what we can do is measure them all, but in one single analysis. This is very important because we can measure different processes that are taking place in the brain in one single go. What happens is that obviously lumbar puncture is not what we like the most, all of us, but that's why one of the revolutions that has taken place in recent years in Alzheimer's disease is the development of the plasma or blood biomarkers. Those biomarkers can be taken or measured with a simple blood test. And although we are not yet at the same level than with the CSF ones, we can measure many things already there, although they have just been developed in the last 5 years. Apart from seeing if it's an image or a fluid, we also have the type of biomarkers depending on what they are measuring. This has been mentioned before by Professor de Stroop. We have amyloid markers that show us the plaques. We have biomarkers that show us the neurofibril tangles or tau. We can also see the neurodegeneration with the NFL, synaptic dysfunction, and since very short time, we also can even look at other co-pathologies as the nuclein phase. And also, as the professor said, we can also look at, in different biomarkers, how we have the microglia and these other cells are altered, or the astroglia that are other cells that we also have in the brain. And I show here some small points so that you can faces, so that you can put a face, so to speak, to the people who are doing this job, especially in our group. And now I'm going to say how we use those biomarkers in Alzheimer's setting. I'm going to talk about their relation with the pathology and how they are also used in the diagnosis workup. I would like to add something here because the landmark when we talk about pathology is the neuropathological analysis. This means that we have to choose the brain of somebody, of course, when that person is dead, and we measure the pathology or different biological processes that have taken place in this brain. And this is, so to speak, well, we have to be as close as possible to that landmark. And this is the cause due to which the biomarkers normally are validated against those lesions. And I'm going to show exactly some of these studies. First, we're going to focus on the amyloid markers, and we are going to see a couple of studies. In these curves, what we can see, although it's not too clear, is that there is a great precision between the biomarkers of amyloid and the amyloid plaques that we can see in the brain when these studies are done in the neuropathology department. And the other interesting thing, what we see in the other figure, is how we can see the different types of PET amyloid depending on the amount of plaques we have in the brain. We can see in the first row that there is hardly any pathology. Everything is blue. There are no dark brown spots as we saw before. So the PET amyloid is completely normal with these blue and greenish colors that are the normal ones. Whilst when we go down to the last row, where there is a lot of amyloid pathology with these brown spots or purple spots, this is translated into an abnormal PET amyloid with those red colors and yellow colors that indicate a high degree of pathology. When we look at the tau pathology, when we look at this pathology accumulated in the brain as tangles, the biomarker that we can use is the PET tau PET. Here we have a similar example. We see the examples of tau PET from greater pathology to lesser pathology, and we can also see the neuropathology in the lower part. You can see that there is a high pathology with these brownish colors, and this is translated into a reddish color in the tau PET in the areas where these pathologies has been accumulating. Whilst in the PET to your right, what you can see is that there is no pathology, practically no pathology in the areas that are measured and seen, and this is tau PET that is completely normal with these greenish colors. This is a study done by Osen Kopele not too long ago, where he gave numbers or figures to these images. Those people who had an Alzheimer's dementia had this tau PET that it was much higher, that level. And the same thing for these individuals that we call who have impairment, mild cognitive impairment, whilst the controls and other pathologies that are neurodegenerative but that are not Alzheimer, that tau PET was reduced. So we can say that the tau PET is very specific for Alzheimer's disease and also very sensitive for it. And here we can see another study where we can see very clearly from people who have tau pathology that's quite obvious here, whilst in the last row you can see a tau PET that is completely normal. So the dementia of this participant is clearly not unrelated with Alzheimer. And here, a very recent study from our group of Smith, where we focus on the clinical setting. And what he did was to see how people who were recruited for our studies, if we did a complete study of all the biomarkers that we used, we asked the physician to give a diagnosis. And then we gave the same physician the result of the tau PET. And we asked him again, what is the new diagnosis, bearing in mind that tau PET, although he already had the previous information. What we saw was that there was a significant change in the diagnosis and as well a change in the management of the patient, change in the medication. So what we can see is that the tau PET is extremely useful in the clinical setting. And here we come back to the tau PET, as I said before, and its regional patterns. We have, as we've said, it seems that the tau protein is accumulated in certain regions in an orderly manner, but not always so, unlike what happens with the amyloid. The tau protein, although normally follows this pattern, can be accumulated in different regions, as we can see in this picture. The most interesting thing is that the tau pathology is very related with the brain atrophy and thus with the clinical symptoms. That's why if we go and look at this figure to the upper part, a typical case of Alzheimer, the areas that are involved are the mid-temporal areas that include the area of the hippocampus that is a basic structure for memory. And that's why one of the first symptoms and more typical symptoms of Alzheimer's disease is the loss of memory. Once, if we go to the pattern nearby, this logopenic appearance has a more asymmetric component in the left zone and in the parietal area of the brain. That area is the one that controls more the language. That's why those patients have more problems with language than with memory. That's why the tau PET can be very useful, because it can give us an idea about the symptoms that it is associated to. And this is a study that was made by our colleague Vogel, where he said that those patterns could be classified with a machine learning method, and they could also be associated not only with the symptomatology, but also with demographic features as age or certain genetic features as well. So it seems that those are very important. And now we have spoken about the tau pathology, the accumulated one, but it's also important to see the tau pathology in the soluble form. What we are measuring here is the hyperphosphorylated protein that we can see both in the cerebrospinal fluid and in plasma. Here we did the study where we looked, well, I'm going to focus basically in plasma because this is the most interesting and new right now, as far as we believe. What we see is that the biomarker that is one of the most specific that we have at present, the plasma p-tau217, is related with the lesions that we look at in neuropathology, both in amyloid plaques and also in the tangles of tau pathology. And here in this study, what we saw was similar to what we saw with the previous study of tau PET, that the biomarker in plasma was high, elevated in the cases of Alzheimer and cases of mild cognitive impairment, but totally normal in the cases of controls or in the degenerative diseases that were not non-related with Alzheimer. And this makes that there is a high precision in differentiating the Alzheimer pathology from the non-Alzheimer, as we can see with this curve that is nearly a square. And here is a study that has been recently accepted. What we wanted to compare here was the biomarker in plasma with the biomarkers that are used at present in the clinical setting, the lumbar puncture and the extraction of CSF. What we saw was that in the biomarker in plasma had a precision that was very high, 90%, and was comparable, strictly comparable to what we have with the current biomarkers in CSF. That's why what we can see here is that it seems that although they are not completely ready, those biomarkers can come to the clinical setting in not too far future. But until now, we have talked about people who are very selected. We are talking about people that go to a clinic, but they are recruited depending on if they have or not other pathologies, core pathologies. Normally, these are people with a social cultural level that is high, that take care of themselves, etc. What happens if we use those biomarkers with, well, people from the real life or real world, a person that comes to the primary setting, and we do all these biomarkers? Is it equally useful? But in this study that Sebastian is doing right now, that is revolutionary, in my opinion, we saw that the p-tau217 biomarker has also big precision in diagnosing or in showing who has Alzheimer pathology and a non-Alzheimer pathology. And it's a very interesting comparison, the one we have in green. This is the PCP the primary care physician. And we can see that whilst the p-tau 217 has a precision around 90%, the primary care physician only had 60%. So I'm not saying that we have to replace the physician, but what I say is that we can help him with a simple blood test. And now we're going to talk about the disease staging. This is very much used to know in what moment of the disease, not only if there is disease or not, what is the stage of the disease that we are in. And this is very typical for oncology, with a typical tumor node metastasis system, TNM. Can we do the same in Alzheimer? Yes, these are the typical studies that were done a few years ago, and that where we had that pathology in the brain using images in order to classify those patients in a time scale of the disease. But as I said, those images are costly, and it can't be done both at the same time, or at least not in the clinical setting. So we wondered in that study, can we transfer this staging or this clinical stage with biomarkers in the fluid? The response is yes. So what we used in this study is we used different biomarkers, in this case in CSF, and we saw a categorization. And what we saw is that those stages that were based on the liquid were correlated very well with the cognitive stage. That means with what we have here in the middle, those that were in higher stages had more probability of being at a dementia stage. But not only that, we could also predict the future somehow. We can see here that in the last picture, that those who are in higher stages, in the reddish colors, had a much higher probability of progressing to dementia compared with those that were in lower stages. Obviously, this is in CSF, and we hope that we can transfer that to plasma in the future. And we keep on with this prediction of the future, the prognosis. Obviously, for the patient and for the family, it is very important to know how this disease is going to progress. What am I going to be able to do in the future, 2, 3 years, or 5 years? Well, in order to do that, it's important to work on these biomarkers that can give us some information about that. In this study, they took participants with cognitively healthy, and they were done an amyloid PET and a tau PET. Those participants that had tau in the brain, here we have then the green square or dark blue, had a probability of progressing to mild cognitive impairment that was much higher than and progressed more rapidly than those that only had amyloid in the brain, here in light blue, or that didn't have any of those two pathologies. So we can predict what can our future be with those biomarkers. As I've said, tau PET is very costly. Can we do the same thing with plasma? Well, in this multicentric trial that we are carrying out right now is that we see that the prediction we can do with plasma and 217 is very similar with tau PET. So it seems that we can do a lot of work already with those biomarkers in blood. And in order to finish now, a brief idea about the clinical trials. The biomarkers can be used in two great categories when we talk about clinical trials. The first one, in order to select those participants, we have to think that the recruitment in the clinical trials is one of the most costly parts, both due to time and money. So pre-selecting them would be very useful. And secondly, we can use those biomarkers in order to see how this treatment works. Well, this study was done by Wagner Brum, and the only thing he did was to develop a possible pipeline in order to try to reduce the costs and the invasion of the tau PET.
So then he classified the patients using a plasma biomarker, as a moderate to high risk of having the positive tau PET or below the low risk of a positive tau PET. With low risk, didn't go to further PETs. They were removed from the study, but moderate to high risk underwent PET, the tau PET, and according to the result, they were recruited or not. And it decreases enormously the costs, both from a personal point of view as monetary costs. And this is my last slide. This is the plasma protein tau 217. In one of the clinical trials I mentioned, they saw that this biomarker in plasma p-tau 217 dropped drastically and quickly in the treated patient, and in the placebo, it kept stable, even experienced a little rise, which suggests this biomarker is correlated to the therapeutic effect of this drug. However, there was another posterior study, and we saw that the changes of the biomarker in blood did not correlate with the other biomarker, which is the amyloid PET, which represents the amount of neuropathological changes in the brain. So it seems that these tau PET are not excellent yet. They need fine-tuning. So Alzheimer's biomarkers do help us improve diagnosis, prognostication, as well as the patient's treatment. The current biomarkers that we have now in cerebrospinal fluid or image biomarkers are very useful, but they do have disadvantages. They're expensive, they call for infrastructure, and they are invasive techniques. And very clearly, biomarkers in plasma will be a great alternative, very useful in a near future to help us with diagnosis, staging, prognosis, and for selecting patients for clinical trials. However, we require much more research, especially in a larger population. And final comment, biomarkers, as you have seen during my presentation, are very, very important, but they shouldn't be considered as a single number to decide on an isolated basis. Of course not. We need a clinical picture, a physician's assessment to consider the globality of the context of the disease, to know exactly what's happening with each of our patients. And now I'd like to thank the group of the clinical and investigative teams, and here are my contacts if you wish to talk to me.
Muchas gracias a Gemma.
Well, thank you very much, Emma. That was incredible, the research at your postdoctorate paper, very impressive. Now we are listening to Alberto Lleó. He directs the neurology department of the Santa Creu Sant Pau Hospital at Barcelona. Dr. Lleó has a degree by Barcelona University and specialized in neurology at the same hospital, Santa Creu Sant Pau. Then he had a doctorate at Barcelona University, and then he continued with his basic and clinical research in memory disorders at the Massachusetts General Hospital in Boston. Then he has clinical activity with translational investigation in dementia, specifically focusing on the molecular basis of the disease and the development of biomarkers. Some of his main contributions are the discovery of new genetic abnormalities in Alzheimer's, the gamma secretase complex in the assessment of new biochemical markers, and frontotemporal dementia. He directs a translational investigation team and collaborates with national and international groups and coordinates the Alzheimer program of the CyberNet. Thank you very much, Alberto. You have the floor. Thank you. Thank you very much, Erika, for introducing me. Good afternoon, everybody. I have to start by acknowledging and thanking the Ramón Areces Foundation and the Springer Nature Group for having invited me to this fantastic meeting. And also, I would like to thank you for choosing one of the best topics, new biological treatments in ID, now that the field is experiencing a boom. And I always finish with the same question. When are the new treatments going to come? And we always said 5 years. But you look at the records, and it's been 25 years that we're saying 5 years, right? But now there is a landmark. There is some hopes for light at the end of the tunnel, and a great deal of hope, yes. Here are my commercial disclosures. Whenever we talk about treatment, I'm a consultant for the majority of the pharmaceutical companies that are developing treatments. And I've also been the principal investigator for the Clarity study with lecanemab, which is the phase 3 study, which is the first approval by the FDA as treatment. The other speakers have discussed fantastically the biology of Alzheimer's disease. I won't repeat. I just want to remind you that I'm going to focus on biological agents in 2 targets, the amyloid and the tau protein, because those agents have yielded the most positive results in the past few years. Okay, Dr. Salvador has mentioned and explained brilliantly that the change in the past few years is that we can measure the biology of Alzheimer's disease with many different biomarkers. So we have like a glimpse of what's happening inside the brain. Neurodegenerative diseases are microscopical diseases, so it's very difficult to know what's happening during those decades. This disease takes 3 decades to develop, so it's an opportunity to gain an understanding of what's happening within the brain. I'd like to talk about CSF biomarkers. We've been working with biomarkers. Now this is a routine test. And CSF testing has been key for our diagnosis. For the first time, we have the certainty that we can confirm the biology of the disease within the patient. And therefore, we can have a much more accurate diagnosis than what we used to do 20 years ago. This biological diagnosis can be carried out even in people who lead very normal lives, and even working, and only their family or surrounding people have noticed a few symptoms. And this is a great change in our approach to this disease. There is a lot of stigma. Many people reject the diagnosis or don't want to admit to the diagnosis. And this is one of the main barriers that we'll have to overcome in the future. We have fought to introduce CSF testing as a routine. There were ethical arguments. It was invasive. They were elderly. We shouldn't do so many lumbar taps. Well, the same arguments will be entertained, that's for sure, when we discuss new treatments. Gemma Salvador has explained that now we have biomarkers in blood. That's the great revolution, and we're working to introduce them into the clinical practice. They're still under research, but in some hospitals, by the end of the year, we will apply them for routine clinical practice. And even before treatment, I like to explain this slide. This slide was a review when I was a fellow at Boston in 2006 with my mentor, John Grandon. This has been the most cited reviews in my personal CV. I'm showing this image. Almost 20 years have gone by, but in Spain, in Europe, the treatment we prescribed in 2006 is still very much up to date in 2024. There's a few changes in formulations. We only have these 4 drugs that have a symptomatic effect. They may mitigate them, but the progression of the disease will advance since they do not act on the causes. Well, fortunately, the situation is changing, and after so many decades, trial and errors, we're bearing some fruits, and also because of the sustained investment, both public and private investment, that together with the advances in biomarkers, we could have some approved drugs. This is a review that Dr. Cummins provides every year. It summarizes all the different trials for Alzheimer. Just two ideas. There's 141 drugs being investigated in more than 187 trials for Alzheimer's disease. Many different strategies are being entertained against multiple different targets. Almost 40% are disease-modifying drugs. The majority of the research is focusing not on dealing with the symptoms, but to try to deal or treat the causal factors that we know are important in the pathophysiology of the disease. We could talk about amyloid and tau, talking about the drugs in pipeline, but there's only 60% of the studies that focus on the amyloid and only 90% on tau. The majority look for other therapeutic targets: inflammation, neurotransmitters, synaptic plasticity, neuroprotection. There are many different strategies investigated nowadays, and we'll hope to witness their fruits in the next coming years. The amyloid and the tau were the first to start, of course, the ones that made it so far to the end of the tunnel. Let's discuss amyloid first. The beta amyloid, to be more accurate, is the main component of the amyloid plaques. It was quite controversial in the beginning, but now we know that it plays a key role in the pathophysiology of the disease. And if we go back in history, the hypothesis of the amyloid peptide was identified and described in 1984. In 1991, we discovered the first mutation in the amyloid precursor protein, APP, leading to Alzheimer's. So now we can associate this gene with the disease with genetic testings unequivocally. But this is very rare, only 1% of the cases, but it does show an association between the gene and the protein to the disease. And now in the year 2023, in the FDA in the States, we approved the first anti-amyloid drug, lecanemab. So almost 40 years have gone by. And if you consider other treatments, a much shorter time took place. This is a very complex disease. We didn't know much about pathophysiology of the disease with limited investment, certainly much less than in comparison to oncology. And that's why it took us 40 years to get it. But this is just the beginning. Many more such treatments will come in the next coming years. So this is the first success, the first big success, lecanemab. We have to acknowledge Dr. Lance Lanfeld at Uppsala, specialized in geriatry, investigating these monoclonal antibodies. And he's responsible for the existence of this treatment, definitely. Dr. Lanfeld had a laboratory, and he described a family that had a mutation in the APP, the Arctic mutation. And exploring these members, they had unusual amyloid plaques. Instead of the classic plaques, they look like a ring with the central part missing. These are very unusual plaques, ring-shaped. They analyzed the composition, and they could see that there were protofibrils of amyloid. They were different, and they were very toxic, and these protofibrils were toxic and therefore giving rise to the symptoms in this family. Then he created antibodies against these protofibrils, and he could see that they could bind specifically to the protofibrils. And he started a research line, which is lecanemab, the humanized version of these murine antibodies, and he created BioArctic company. And finally, he leverage on the knowledge of this antibody to test it in humans. This is the phase 1 in this company, then phase 2 with lecanemab. Phase 2 is when we look for the best dose of the drug, and this is something interesting. The most effective dose as to the reduction of amyloid was every 15 days intravenously. This has huge implications. It means that lecanemab now is being administered IV every 15 days. It started for exchange with oral medication every 6 months, and now a person has to come to hospital every 15 days to get the intravenous infusion. Well, we selected the best dose, and then after Biogen, because clinical trials are so costly, they called on Biogen almost 900 patients in each of the arms. And finally, they went to phase 3. Phase 3 was the pivotal study, the Clarity clinical trial. The Clarity study, we participated at the San Pao Hospital, like many other Spanish centers, and it was the registration study. It confirmed that lecanemab, for the first time, showed efficacy in Alzheimer's disease. 2 images from the Clarity trial. On the left, the effect on the amyloid burden. In blue, the placebo, measured by amyloid PET, and in yellow, the treated patients with lecanemab experienced a drastic drop in amyloid burden in the brain at 18 months. The anti-amyloid effect of reducing amyloid burden is very, very relevant, quite fast, and almost complete clearance. And the other efficacy variable is a very well-known scale, CDR-SB, measuring cognition and functionality, widely employed. And the placebo in blue obviously declined at a faster rate than the lecanemab treated in yellow. We have to show it in graphs. Does it slow down the disease? Does this reverse the disease? I think that the graph shows very clearly that it does progress. It goes on progressing, but at a slower pace, at a slower rhythm than the people treated with placebo. And we get this 27% of slowing down, which is very important in a year and a half, 27% of slowing down. Not improvement, but reduction of progression at 18 months. When we explain this, it's more or less 6 months. 6 months gain additionally in functionality being preserved in the clinical history of the patient. And then the amyloid beta in plasma or in p-tau, either in plasma or in CSF, there's a great improvement with lecanemab in the biomarkers that reflect the biology of the disease, with tau pathology, amyloid deposition, synaptic markers, several biomarkers exhibited more or less the same behavior. It was all consistent. However, there were adverse events. And the adverse event most reported, the most feared, is what we call the area effect with edema or hemorrhage, right? And we can see that some patients do develop these areas of brain edema. The antibodies generate permeability and then lead to this focus of edema or hemorrhages, point hemorrhages that are also occur spontaneously in AD, but seem to be enhanced with the use of these drugs. This is very serious and it concerns, but we actually have so many patients in the clinical trials, and the majority of them are asymptomatic, and recalling 1 or 2 doses, these abnormalities disappear. They normalize. However, if you are told that you have microhemorrhages in the brain, you get scared, and some people wish to drop out from the study for this reason, of course. And we really have to explain these adverse events so that the people can understand. There are some extreme cases. We haven't had this at our hospital, but there are descriptions of a case that had a stroke with the hemorrhages because of lecanemab. In this instance, it led to death. When these treatments are commercialized, we should carry out a campaign of education of the population as well as the healthcare personnel at the hospitals, because there might be serious and fatal adverse events with these medications. The next one. The first one was approved by the FDA. They have a few months' experience with it. And, I mean, lecanemab, and we're learning how it's being delivered in the States and how the memory clinics are dealing with the situation. There's so many challenges. And now, the second success story, donanemab, an antibody against the beta amyloid, but it is different. They have this modification of the pyroglutamate peptides, which is modified and which is found in the amyloid plaques. And this is important because it's not a single amyloid that can be treated. There are many different strategies to different amyloid species that may be successful. So now we have the phase 2 study, the Trailblazer, replicating the effects of lecanemab. There's a very drastic change of the amyloid plaque with donanemab or the brain in green, and a certain cognitive study. In phase 2, you do not show efficacy. That's not the statistical power or design, but it gives us a glimpse, right, an indication of some hopeful results. Nevertheless, we always need the phase 3, much costlier, very huge. And in Trailblazer phase 3, we replicated phase 2. There was a reduction of the progression, like about 30%. And in a group, it reached down to 35%. It was a very creative design. Lilly decided to include 2 types of patients according to the tau pathology. Obviously, they all had to have amyloid deposits, but they broke it down into low to medium tau, according to the tau PET, and the other one with the high tau levels. That's very relevant with the high tau deposition. Biologically speaking, notwithstanding the clinical symptomatology, will be more advanced in the stage of Alzheimer's. So what's really interesting is that the benefit of the drug was greater in this group with low to medium tau burden. And yet, the high tau had a much lower benefit, virtually non-existent in some cases. So what's the take-home message? We must treat people in the initial stages of the disease with these drugs, in initial stages based on biology, not on the emergence of symptoms of the patients. And this is a study, Trailblazer phase 2, designed specifically to answer this question. And finally, tau studies. Tau studies, of course, lag behind the amyloid studies. The tau is much more complex as a protein. Its structure is not so well known, and there have been many failed studies, unfortunately. But I would like to show this highly hopeful result from Biogen, Ionis Pharmaceuticals. It uses an antisense oligonucleotide, a sequence of oligonucleotides that lead to a decreased expression of the tau protein within the brain. It is delivered intrathecally. It must be delivered into the CSF. It diffuses, and then somehow it inhibits the production of the tau protein. We close the tap, so as to say, so that it doesn't accumulate in the brain. The outcome of these studies have been published in congresses and magazines. And it shows that for the first time, we can eliminate the tau depositions within the brain, measured in this case by tau PET. Treated patients, as you can see, have a lower tau burden than those treated with placebo. Obviously, the tau deposit will accumulate in the case of placebo. What's the working hypothesis? Certainly, it is a very surprising result because it shows that these injuries are not so irreversible as we thought. If we close the tap and there is no more tau production, the microglia and the clearance mechanisms within the brain can eliminate it. This is a huge conceptual change. They're much more dynamic than we thought. So far, the necropsy studies gave us the impression that these lesions or injuries are very solid, very well established, and it goes to show that they're much more dynamic than what we thought, which is a great hope for anti-tau treatment. And this is linked to a report last year with a doctor from Edinburgh, showing that tau, the soluble form of tau, which is believed to be the most harmful, the most pathological, is accumulated in many parts within the brain and also at synaptic level. We use high-resolution microscopy with special techniques. These are synapses. You can only see them by using these special techniques. And within the synapses itself, we find the tau protein, but it is the soluble tau protein. And because of its morphology, it is more harmful and deleterious against the synaptic worse than the better-known, more aggregated types of tau protein. And now some technological advances. In Alzheimer's disease, we have different factors. We have a better knowledge of the disease as has accumulated in the last decades, and then technological advances. In plasma and the protein assays and detections were always there, but now we haven't measured them, right? Well, here we have other technological advances. Here is a study with the low-intensity focused ultrasound. And it is mediated by US. LIFU technique, and we're using it for tremor. And with this ultrasound, you can induce the treatment, and you can do it with the antibodies because they usually don't cross the barrier, less than 1 or 2%. So we open up the blood-brain barrier so there is a greater penetration. They apply the ultrasound on a side of the brain. They open the blood-brain barrier on that side, and in that side, there is a higher penetration of antibodies, and therefore there is a much greater clearance of the brain side that was open with the ultrasounds, right? Will this be applicable in clinical practice? No. It's a proof of concept, but it shows that we are gaining entrance to this virtuous cycle because of the knowledge we can leverage on the technological advances in other fields. What do we expect? The present and the future. It's a future for us, but it's the present in the US. Lecanemab has already been registered by the FDA. July 23, they already started prescribing it to patients. In the next months, it will come to Europe, more or less by April. The FDA will rule on donanemab in the next few weeks. The European agency will deal with it in July, and there are other strategies, of course, with other targets. What is the situation in the States? Here it is. It's from the ALS Forum web. Here are the number of infusions. It's a snowball effect. The patients do have to come every 15 days. And we increase the number of new patients, and now they're on the verge of collapse in the infusion centers at the memory units. There's just too many patients coming from the infusion. There are so many challenges. Now we have a golden opportunity witnessing what's happening in the States. We should prepare the infrastructure here in Europe in order to deliver the drugs appropriately to our patients. Conclusions. I hope I have convinced you that we're entering a new era. We have lecanemab with the first biological agent as a clearly positive agent that is a disease modifier treatment. In the future, we will have donanemab, which is important to treat patients in the pathological initial stages without symptoms, and what happens in the long term, 4, 6, 5 years. Is it a benefit that will increase or decrease? We don't know the answer. We will see in the next coming years. And I think it's also important, besides other multiple strategies, now we have the golden opportunity to adapt the infrastructures of our own hospitals in Europe to be able to cope with the huge challenges awaiting us that bring so much hope for our professionals and especially for the patients and the family. And I'd like to thank all the members of the memory unit at San Pao Hospital.
Thank you very much, Alberto, for all these hopes and this open door to the new technologies and the new drugs. We are going to finish. This is the last presenter before the discussion. Please don't leave. And it's possible that we have left the best for the end, the prevention. What can we do right now, all of us, in order to prevent those diseases? I would like to introduce Professor Jill Livingston, who works in the Department of Mental Health in old people from the University College in London in the United Kingdom. Dr. Livingston is chairing studies in people with dementia confirmed and with suspicion of developing it, and also their relatives. Their family, his work is interdisciplinary, focused on the epidemiological and psychosocial research applied to dementia to clarify the mechanisms involved in its development and co-design and try interventions. One of the most important things that Dr. Livingston did was we're chairing the Standing Commission of Lancet on Prevention, Intervention and Care to Dementia that has already been published in 2017, 2020, and the new one that will be published now in 2024. They did new research and meta-analysis on the risk of developing long-term dementia and a global assessment of the current evidence as to the interventions done. In a very important manner, this type of studies have also given rise to changes in the different policies and in the behaviors about how to treat the dementias. In Jill particularly is also researching on interventions to help and improve the life of patients and their families, and especially interested in the minority populations and the populations that are not taken care of. Thank you very much, Jill.
Thank you very much. I hope you can hear me and that my accent doesn't prevent translation. So I'm going to talk about the evidence that we can prevent dementia and what should we do. And this is mainly from 2 Lancet commissions, and the third one is due out this summer. And it's not just me, there's a whole group of people from around the world who have different roles within it, who have different jobs, and give us some balance and knowledge. And at the bottom are our partners who have funded the work that we've done. So I'm going to talk about why we should consider dementia preventable and the risks for dementia and what we should do. So I'm not going to go through what people keep telling you is that there are more people with dementia, as fortunately fewer people are dying at a young age. However, despite this, if we look at the age-related incidence, that's the number of people per 100,000 of a particular age who've got it. In Europe and in the States and in high-income countries, there's been a 25% decrease over the past 20 years. So when Bart's talking about our reduction that we might be able to have in the States to prevent us having to have so many people to treat, and because so few people, nobody wants to have dementia, there's a lot of evidence that that has been happening. However, as the risk factors change, that could reverse. Nonetheless, dementia has been stable or increased in some countries, in Japan, South Korea, Hong Kong, Brazil, India, and Taiwan. So that means that dementia is potentially, but not inevitably, preventable. And the two mechanisms which overall are expected to reduce it are cognitive reserve and reductions in damage. And I'll talk more about cognitive reserve in a second. Improvements so far have been in higher income, more educated people within high income countries and men more than women. So in low and middle income countries, there's massive potential. In some high income countries, there's massive potential. And in all high income countries, many, many people have not had this reduction as they've had less income, less education. So this is a graph of neuropathology of people who have or do not have dementia. If you look in the bottom left-hand corner, you will see that, as you would expect, the more neuropathology, it doesn't matter what it is, plaques and tangles that people have talked about, infarcts, Lewy bodies, the more you have, the less your cognition is, the more likely you are to have dementia. But if you look at the four other graphs, which have, these are individuals after death in neuropathology, you'll see that the amount of neuropathology overlaps, so that some people with high cognitive performance have as much neuropathology as some people with late dementia. And this is what we call cognitive reserve, the ability to tolerate brain changes without developing dementia. And if you have high cognitive reserve, then you can tolerate it. And one of the ways is to keep thinking, keep doing things. So I'm hoping that we're increasing the cognitive reserve of the whole audience tonight. So we've talked about, in the last Lancet Commission, 12 risk factors which have excellent evidence that they are risk factors for developing dementia. And that's developing all dementias, because as Bart talked about earlier, most people have more than one neuropathology when they develop dementia. And we looked at them in early life, midlife, and late life. And I'm not going to go into details because I haven't got time. But for example, people who are overweight in midlife are more likely to develop dementia. But as people begin to develop dementia, they usually lose weight. So in late life, some people are thinner because they're already on the path to dementia, rather than because, and their lack of obesity is not a risk factor, but is actually part of their illness. So I'm going to talk about some of these risk factors here, and I'd like you to think about them and work out that people are not like rats. So people often have more than one risk factor, and they tend to cluster together. So we work out how important a risk factor is in the population, and that's called the population adjustable fraction, the population attributable fraction, and that's a fraction theoretically prevented if you could eliminate the whole of the risk factor. And it's calculated, it's slightly more complex than this, but approximately by the relative risk. So how big a risk it is having this problem, by the prevalence of the risk factor. So the more common it is, the more important it is for the whole population. And to do this, we used all-cause dementia and international data to think about how common it is. But of course, things do vary between countries. We talked about 12 risks, but we know there are others. We're just being very conservative in terms of the risk and thinking about ones which there's really good evidence. And we adjusted for this communality because people are not lab rats and tend to have several things at once. And we came out with this population attributable fraction throughout life. And maybe the most successful thing I've ever done is to get someone to draw this diagram, because I never go to a dementia thing without seeing it. I've got a new one for the summer. But what I'd like you to notice is I was initially astounded to find that the most common one was hearing loss, and this was followed by less education and then smoking. And if you add these together, they make 20%. So half of this overall 40% potentially avoidable dementia is accounted for by these three risk factors. But the other ones are still there and still important. Even if they're a small percentage, there are a lot of people because dementia is so common. And I just wanted to show you what happens if we weight the population attributable fraction, taking into account that people tend to have clusters of risk factors. So less education, if you just think about it as one thing, is 19.4, but adjusting for the fact that people with less education are more likely to have other problems, then it's 7.1. Similarly, hearing loss reduces from 22 to 8, and smoking from 14 to 5. So whenever you hear somebody say, well, people with this problem are more likely, much more likely to get dementia than others, ask yourself and ask them, did they take into account what other risk factors they had? I'm now going to talk about some of the risk factors. I'm going to start with hearing loss. When we first published in 2017 that hearing loss had the highest increase in population, had the highest population attributable fraction, there was a huge amount of doubt about it, but a lot of people have done a lot of research since then, and I think that now people don't tend to doubt it. I think the important thing is what's the effect of the use of hearing aids? And in JAMA Neurology in 2022, a systematic review and meta-analysis of the use of hearing aids found, which they had 126,903, so a lot of people in it, and the follow-up between 2 and 25 years found that people who used hearing aids compared to those who did not had about 20% lower risk of cognitive decline. That's people with hearing problems, and a 17% lower risk of dementia. This doesn't prove that hearing aids prevent dementia, because it could be the sort of people who use hearing aids are the people who have more money, who are more able to sort their lives out, have more support, but it does indicate the fact that they seem to make a difference. It does indicate that it might make a difference. And similarly, another study showed that people who had mild cognitive impairment with hearing loss, those who used hearing aids, took 4 years to develop dementia on average, and those who did not took 2 years. So again, a suggestion that really it makes a big difference, and practically in our clinics, we should be saying to people, think about your hearing. There's been one randomized controlled trial, and this is called the Achieve trial. It came out in the Lancet recently from Frank Linnetal in Johns Hopkins. It was very interesting because most of the people that he recruited came from adverts. It didn't have any effect on the it didn't have any effect using hearing aids over 3 years. And one of the reasons it may not have had any effect is that the people that he recruited didn't decline, the people from adverts. And people from adverts tend to be extremely healthy. I don't know how you all got here tonight, but maybe it was advertised. They tend to be people with initiative, reading adverts, acting on them, sorting out things. However, there's a pre-specified analysis looking at a group that they had recruited many years before, and it made a huge difference over 3 years. And these were people who, these were people who had not answered adverts, and they were older, they had lower baseline cognition, they smoked more, they had less education, and they more often lived alone, more likely to have diabetes and hypertension. So they were a group who had lots of risk factors. And interestingly, the difference was more than you would predict. And what we don't know is, and they're going to analyze it further, was did the high-risk groups who had hearing aids, did they change other things? Did they start to have more social contact? Did their mood get better? Were they able to go out and do more things? Did they go and see doctors and sort out their things when they could hear them better, and more motivation? Moving on to education. We've known for a long time that education is related to having a higher cognitive reserve. And people who go to school for longer are more likely to have a cognitive reserve. And they however, for many years, we haven't been sure whether it's just people who have more education do more cognitively stimulating things in later life, or whether the cognitively stimulating things in later life make a difference. My colleague, Mika Kivamaki, did this study with several other people like myself, and he was able for the first time to see a huge number of people who didn't have much education but still had cognitively stimulating jobs. And what he found is that having not much education but a cognitively stimulating job decreased your rate of dementia by 20%. People with both, with more education, it was decreased by 27%, so it looked like earlier life was a bit better than later life. And people with both had a 37% decrease dementia risk. And he looked at the proteins and found that the proteins that the people who had more cognitive stimulation, that 20 years before the ages of people got dementia, they had increase in the proteins which increase their axonogenesis and synaptogenesis. So it looked like a physical change that made a difference. And there's some evidence that retirement may increase deterioration even if we allow for ill health, because obviously people with ill health retire earlier, and that's interesting. But countries with lower rates of with lower ages of retirement, people tend to do worse and develop dementia earlier. Moving on to smoking. Smoking was the third most important risk factor, and smoking is, I mean, you won't find a doctor who doesn't tell you that smoking's bad for your health. You won't find anyone who doesn't tell you. In most high-income countries, cigarette smoking is decreasing, but it's not decreasing in some of the lower-income countries. It's increasing as there's more and more adverts and people might have a little bit more money. However, there's been 2 studies. You can't do a randomized controlled trial of stopping smoking because we've got to tell everyone to stop smoking. But there's 2 studies, one in Britain and one in Korea, and both of them showed that ex-smokers, people who'd stopped for a couple of years, had reduced their rate of dementia to that of the baseline population. So I'm saying it's never too late to stop smoking. Just as your risk of cancer goes down after you stop smoking, your risk of cardiac disease goes down if you stop smoking, your risk of dementia goes down after you stop smoking. I'm just wanting to talk about a couple of other risk factors. I haven't got time to talk about them all, but depression. People who are developing dementia have a more vulnerable brain and are more likely to get depressed. But people who have depression in midlife are also more likely to develop dementia. One big study in the UK Biobank of a huge number of people aged 50 to 70, followed them up for around about 12 years. And in general, people who had depression had a 50% increased rate of dementia, but people who were treated had a risk of dementia dropped. So antidepressants and psychotherapy both dropped the risk, and combination therapy decreased the risk compared to people who continued to have depression without treatment. But also those who were untreated but got better also had a better prognosis. So I'm suggesting that energetically treating depression is good not just for your quality of life then, but also for the future and reduction of dementia. I'm going to move on to air pollution. On the way here, I understood the driver told me that in Madrid you have to have a special certificate to drive to say that your vehicle is not particularly polluting, and that's got to be good for the whole population. All studies show that air pollution, what they call particulate matter, increases the dementia risk, and that comes from gas, oil, diesel, or wood. And it comes from transport, from industry, and quite surprisingly for residential wood and coal burning stoves, which some people have as a sort of lifestyle choice rather than because they must. There's been several studies in China, in France, and in Canada, all of them looking at naturalistic studies in areas in which you have a decrease of air pollution, and all of them find that it helps cognition and decreases the risk of dementia. So again, this isn't something we individually can change, and people don't choose to live in highly polluted areas, but it's something that government and policy can make a difference. High blood pressure. Persistent midlife high blood pressure increases the risk of late life dementia. Every time there is a randomized controlled trial of treating hypertension with drugs, it's stopped because the placebo group does so badly in comparison to the treatment group. However, if you put all the evidence together, individual participant data from placebo-controlled trials, you find that treating blood pressure reduces the risk of dementia at several years later. There's only one study which hasn't found that, and it only followed up people for a year, and that probably isn't long enough to really show the difference. So again, 5 years later, 4 years later, 3 years later, there's a huge difference in the rate of dementia. So keep your blood pressure under control. So there's risk factors. Do changing them change outcome? I think the answer is yes, and we get more and more evidence over time. Use of hearing aid decreases risk. Air pollution reduces it, cognition is better. Hypertension treated makes a difference. Jobs with high cognitive demand help. Stopping smoking reduces risk. If we really want to see a difference, though, it's important to make changes for people who are at higher risk, because we can make much more difference. And unfortunately, randomized controlled trials tend to recruit low-risk people, and often we don't really see the changes because and that's true of drug trials as well, because we really need to, if we want to make things, if we want to show there's a difference, we really need to have people who are going to develop the problems in the first place. I just want to show you that it's different in different countries, but it's different in different ethnic groups. This is a study that we did in New Zealand, and unsurprisingly, Maori and Pacific people were at much higher risk than European, and European people were at higher risk than East Asian people. There's a lot of East Asian people in New Zealand. If you look at this as in Brazil, poor people in poorer regions were at higher risk than in richer regions, and that probably underestimates it, because in Brazil you only know you've got hypertension or diabetes if you go to see a doctor, and you only go to a doctor if you can afford it. The United States Congress, NAPA, have now a national plan to address dementia. They added a new goal in 2021 to reduce the burden of risk factors. And they're saying they're aggressively addressing 10 potential risk factors with the idea of decreasing it by 15% by 2030. And they're expecting that 1.2 million fewer people will develop Alzheimer's disease. I'm not sure whether their numbers are going to be right, but they really think they can make that difference, stopping people getting it in the first place. Equally, in Britain, or not equally, but in Britain, stopping dementia is becoming part of the midlife health check, and they think that people change a lot more if you say to them, treating this might prevent the risk you getting dementia, because dementia is the most feared disease. It's the one that people don't want to get because, as the other speakers have said, you lose who you are and become dependent. So my message for everyone is be ambitious about prevention. Disease-modifying treatment will not remove the need for prevention. It's better just to prevent it if you possibly can. 40% or more is potentially preventable. It won't all be prevented, but some of it will. There are clear strategies to help already, that hearing aids, smoking cessation, decreasing blood pressure, decreasing pollution and depression have been shown to make a difference, that tackling risk provides more years of healthy life, so you get a compression of morbidity. And I think that's what all of us want. We don't want to have years and years of being unwell. Sometimes it prevents dementia ever occurring. It also saves money, and I'll show you the health economics if you invite me back. The most vulnerable people in society stand to gain most, and this is something that all of us as individuals and within policy can make a difference. So thank you for your attention.
Bien, buenas noches.
Very good. Well, good night. Thank you. Now we may ask questions of the experts. Okay. I'd like to encourage everybody to ask questions either in English or in Spanish. Can you hear the English? Can you raise your hand if you can hear the English, please? Dr. Debra, thank you. Thank you. Good afternoon. Thank you very much to all the speakers. My name is Juan La Huerta. I'm a member of the steering committee of the Spanish Confederation of Alzheimer's Families Association. Okay? We're extremely interested. Dr. Yeo, and also related to Professor De Strooper, and it was a data that was very encouraging, personally. If we were able to delay in 5 years the onset of the disease, of Alzheimer's disease being symptomatic, we would offset the predictable increase of the new cases in the next 25 years. Okay? You did say that. In Spain, we don't have data, but conservatively estimating, we could say there's 600,000 people with AD for 48 million inhabitants. Not bad, right? But then in the future, the segment of population with the baby boomers from 60 to 65 will reach that age after 2025. The new treatment, lecanemab, donanemab, will modify the disease or the natural history of the disease. They modify it according to these curves that you have shown us. They make the curves run in parallel for a given period of time for 18 months, right? Ranging from 25-30% decrease. So your life expectancy may be 10 years after the onset of symptoms. 30% is 3-4 additional years of life gain, right? Where we shall delay the progression of the disease or slow down the progression of the disease. And I relate this to Professor De Strooper. Maybe 5 years is too much, but now after Professor Livingstone has shown us all the different measures that we can perform to further reduce that 40%, maybe we could do it, right? But despite all that,
4 o 5 años, pero
despite of that, delaying 3, 4, 5 years, people will still go on developing the disease. They will progress in the natural history of Alzheimer's disease, then when they will reach the final stages of the disease, unless they die of something else before. That's probably what you were trying to point out, right? So what about the new treatments? What do we really expect? Are they only for people with early mild disease? What can we expect to change in the long term as to the burden of the disease from a social and healthcare point of view. What can we expect of these future treatments on the tau protein? Will they really influence the course of the disease? Well, as you said, these are just the first treatments, okay? This is the first modifying treatment. This is the first disease-modifying agent. As of today, we've only treated patients who already had symptomatic disease, but with MCI or mild dementia, the initial mild stages of the disease. Those were recruited. But these drugs are also being investigated in symptom-free people with biomarkers that are positive. They do have neurobiology, but still don't have symptoms, okay? There's two ongoing trials, one with lecanemab, the other one with donanemab. If these drugs give appropriate results of efficacy, then yes, we can talk about delay of the onset of the disease or the onset of symptoms. But as of now, we still don't have data. We do not know if we can delay the onset of clinical symptomatology with these two drugs. We have to wait a few years, okay? Because delaying the onset is different from slowing down progression, okay? We should ask Dr. Strupper, since average age is 63, in presentation, if we delay these 5 years, then the people, because of life expectancy, may die due to other causes, so the modeling is complicated. It's an old method for estimation, the impact of treatment on the total number of cases, which is complicated. And now, as to the curves of the disease evolution, yes, they are separated. They don't really run in a true parallel fashion, okay? But they do disappear. And they've been presenting data 2, 3, 4 years with some of these drugs. And it seems that the gap separating the curves increases with time, albeit slightly. We shall see whether it's 27%, whether it decreases or remains stable in time or even increases. What is clear is that the administration of these drugs, when they're finally approved in Spain and Europe, will call for changes in infrastructure, the hospital, day hospitals, MRI infusion chairs, and we don't have that infrastructure right now. This is one of the truths, right? We don't have the necessary infrastructure.
That slide I show was a slide from the Alzheimer Association in the United States, so I don't take scientific responsibility for it, but I think the concept is really true. I think that apart from medication, Dr. Livingstone also showed that changes in behavior could have a big influence. I'm certainly sure that cardiovascular hygiene will give us a couple of years. So I'm overall very positive. And I just wanted to say something about these antibodies also. So the effect is not huge, let's be honest about that, but it is an effect, a clearly demonstrable effect. And so, as I tried to say during my talk, the medication in AIDS, the medication in cancer, it's also started with small differences. And so what we need now to do is to get these drugs to the patients and see who profits more from it and who less. And maybe in a couple of years we need to revise and say it's only to be given to other people. But in the meantime, the industry has seen that it's worthwhile to invest in this. If we now say it's not good enough, forget it, then the stimulus to further develop is away. What I see at the moment is that all these companies now are trying to make a better antibody than the one we have. So so modifications are done to make it now not intravenous anymore, but that you can do it under the skin with a needle, so that the general practitioner can give it, so that you don't have to go to the hospital. That's certainly going to come in the next 2-3 years. And then other groups are trying to make that more of the antibody which you inject in the blood goes into the brain, so you can make a small shuttle on top of that antibody. And then you improve, instead of 1% to the brain, you will get 5 or 6%, which means that you can give lower doses. And then something which I thought very interesting with the donanemab trial was that you treat a patient for a year, you get a new PET scan, the amyloid is away, okay, we stop the treatment, we leave you there, it's a kind of cleaning your brain of it. And then on top of that, we will see new medications coming in along the lines I was talking about, and I will add to this. So you need really to see this as the beginning of a big, big story.
Thanks, Bart.
Sí, buenas tardes. Mi nombre es Concha Aparicio.
Hello, my name is Concha Aparicio. I am editor-in-chief of Active Aging website. I'd like to thank all the speakers and especially Dr. Livingstone. That was a very positive message. Thank you very much, Dr. Livingstone. So, my question is related to that. Worldwide level, it will be very difficult to guess what's going to happen with Alzheimer or dementia in a few years, but it will be less difficult in the high-income countries, right? I mean, I think our perspective would be very different, yes, very distinct from those people who have now 80 or 90 or even older, to what the new generations will be, the new cohorts that are now getting to retirement age. And it will be very different from 10, 15 years. The education level is very different, and it has been demonstrated is one of the heavier factors. So, to what extent do you think this is taken into account in the future estimations of the incidence of the disease? Populations change, maybe it's not enough. Maybe you could comment on that.
Hello, thank you very much. I think that things will change enormously in the future, just as you say. I suppose they changed enormously in the past. Education has been helpful, and more and more people are educated, particularly in high-income countries. Excuse me. But there's still many people who are not. What's happening in high-income countries is that many more people have diabetes, which is a risk, and hypertension. So in some ways, there's increasing risks as well as decreasing risks. And I think that we have to think about it in the policy level as well as the individual level. So people take exercise if they are more likely to take exercise if it's safe to walk around their neighbourhood. People are more likely to not to be obese and to have that diabetes and high blood pressure if it's easy to buy good food within easy walking distance. Air pollution is massively affected by governmental action. So it's not just individuals, but governmental action. But I think there is a lot of hope because we're beginning to know what to do and how to do it. We're doing trials or beginning to do trials ourselves of helping individuals in without much education change in a way that is scalable and rolled out. So I think there's lots of hope. And I think in low and middle income countries, the economic benefit will help sway governments. They obviously want to help people just as in high income countries, but the fact that it costs so much to look after somebody with dementia, and that includes loss of individuals' work, will sway people to do more and more. So I'm optimistic for the future, optimistic that this is the beginning of a drug revolution, optimistic that it's the beginning of a lifestyle and political revolution.
Hola, buenas tardes.
Hello, good afternoon. Thank you, all the speakers. You're outstanding lecturers. When I was in medical school at the beginning of the 80s, things were so different. We were told there was a difference with senile dementia and pre-senile dementia, like Pick's disease and Alzheimer's disease were pre-senile dementia. And we were told AD takes place 20 years before with the same dementia signs than what is the normal aging dementia or senility, because it was considered normal. Why has the paradigm changed? Why? Can you tell me about it? Because it really is astonishing. I can't believe it.
I entirely agree. I'm about your age. I think in the 80s I did medicine and was exactly how it was told. And so the change is knowledge. That's driving it. We understand much more of this disease. I was a witness of how much we learned over all these years. And that's, for me, the biggest reason. So the problem with our job is that it's something which is slow. And so our society wants things changed in 2 or 3 years. But unfortunately, not everything is bioinformatics or finances or whatever. Some things need really a lot of time to clarify and understand. Shooting a rocket to the moon takes time. Building a cathedral costs time. And so finding and solving a disease costs time. So cancer, the war against cancer started in the 70s. The war against AIDS started in the 80s. And so the war against dementia is only beginning to start. So that's the whole reason. So knowledge is the fundamental thing which drives these things forward.
Simplemente añadir.
I just wanted to add, may I? I just wanted to add another historical fact. Augusti, the first Alzheimer case described, was 55-year-old. Thus, it gave rise to the idea that Alzheimer's disease was a disease experienced by younger people. It was only afterwards that neuropathological studies showed that senile dementia actually was the same dementia, but it's true that it took decades to turn down. Good afternoon, Lola Lesma, researcher of the Severo Ochoa Molecular Biology Center. Thank you. Very clear, interesting, and hopeful lectures. I think it was fantastic, this phosphorylated specific tau that can distinguish from other dimensions. How did you find that biomarker, Gemma Salvador? Why? Is it so specific? Are you going to investigate that so that you can understand pathophysiology better? And for Dr. Leo, if you're going to use the tau-specific binding ability as a target for antibodies, okay? Because it's another possibility to develop monoclonal antibodies with a very relevant target, okay? Gemma Salvador. Well, thank you. Thank you for your question. I think it would be very interesting. The quick answer is we don't know. That's too bad. It's a mixture of things. First, we know, I'm sorry I didn't have time to explain.
Solo la forma fosforilada.
It's just the phosphorylated type is measurable, but there's a study of our group where we looked at 10 different biomarkers, different versions of the 217, phosphorylation in a different degree, in a different way, and they had a different precision. It's not the same to measure with mass spectrometry than with immunoassay. So the 217 seems to be very specific to amyloid plaques, and probably that's why it's such a very good biomarker. But yes, we need to deepen research to gain an understanding of why is it happening like that and why is it so specific of the disease. And I didn't have time, but it seems that the 217 is a sort of mixture. It gives us information on amyloid, but also information on tau pathology. So, you know, it seems to be a middle in between, between the amyloid pathology and the tau pathology. We need further research to know exactly how the different fragments and phosphorylation patterns in the tau protein take place and how they correlate to pathology. And especially if we act on a specific one, such as 217, we can delay or modify the course of the disease.
Y respecto a la segunda pregunta.
And as to second answer, the answer is yes. There are antibodies being manufactured against different tau regions. They're under research in AD, phase 1, phase 2, phase 3, with different companies targeting different regions of the tau protein. No positive results so far, unfortunately. There is a controversy because the antibodies don't access intracellular phase, they don't gain access inside the neurons. Maybe the mechanism of action is different. Maybe could be blocking from one neuron to the other, but these are ongoing studies. We're awaiting the results and we really don't know. But yes, they are following strategies of targeting monoclonal antibodies, and I'm very sorry. I have to catch my train. Goodbye. Thank you very much, Dr. Yo. We are slightly beyond time. Maybe one short question, please, here. We really must be closing, unfortunately. Thank you. I liked all the presentations very much. I have two questions. Very easy questions. I thought I had understood that there was this myth or legend that if you have cancer, you will never have Parkinson's disease nor Alzheimer's disease. That's a myth, okay? And another one, which was quite a surprise in Dr. Livingstone's presentation, we didn't have the apocalypse riders such as cholesterol, hypercholesterolemia. And I read that there are some hyperlipidemia genes that could be correlated with Alzheimer as well. Thank you.
It's a great idea to reduce your cholesterol. We don't have much time, so I'm not going to say any more.
Alguien, you want to take the...
Yeah, the lipid story is because of ApoE4 largely, but ApoE4 has multiple functions, so it's certainly important for lipoprotein metabolism. But in Alzheimer's, it's a really major factor in driving amyloid plaque formation. We do not really completely understood, but we did experiments, and the major effect of ApoE4 is amyloid plaque generation. So, and I'm not sure that the link to the lipid metabolism, which is biology, is really going to give us an insight in the treatment. But I agree with Dr. Livingstone that lowering your cholesterol is good for your blood circulation and brain. I should have shown that slide. Your brain is full with blood vessels. So keeping your heart and your cardiovascular system all right is very important for your brain.
Yo voy a ser muy tramposa y haceros una última pregunta.
I will cheat. Okay, my very last question before closing. We haven't talked about the big opportunities of the role of the glial cells, the glia. We talked about the tau and amyloid proteins, but there's a new biomarker, DLP, for the glial markers, and Dr. De Strooper with the clearance of inflammation, and just a few words of this potential new avenue.
I didn't have time to talk about it, but my lab is 70%, 80% working on this new, on these other cells, the non-neurons. I think that's the biggest difference with the classical amyloid hypothesis of extremely simplistic. And so I think that the reason why I think it's so important is also genetics. So I showed you this big cloud of genes. And so you have the causal genes, which are all in amyloid pathway, but all the other genes are almost all, not all, are in the microglia, and they are modulating the way your microglia react to the amyloid. And so that's also why I'm saying Alzheimer's disease is not accumulation of amyloid, but it's the way your body reacts to that amyloid. And that explains why some people with amyloid seem to be healthy, and other people will become very rapidly diseased. So the glia cells are extremely important.
Muy bien, muchísimas gracias por las preguntas.
Thank you very much for everything, for participating, for sharing this, for the speakers. Thank you very much indeed. They were great presentations.